Okay, welcome to the second part of 2 in our podcast on periodic trends. What I'm going to be covering today comes pretty much from section 5.3 in your book. And periodic trends are just things that we notice about the periodic table based on where an element is positioned. We're going to talk about 3 trends, but there are certainly a lot more. When you're trying to explain trends, you're going to use one of 2 different explanations depending on where the elements are related to each other in the table. The first explanation you're going to use is effective nuclear charge. So in the last podcast we said carbon would be a +4, chlorine would be a +7. That difference in effective nuclear charge affects a couple of properties that creates a trend. Right? So we use that when comparing things in the same row. If we're comparing things in the same column, we use the distance that the energy levels are from the nucleus as kind of our explanation, high energy orbitals being farther away. One very important thing to keep in mind is if I ask you to explain a trend, stating the trend itself is not the explanation. The explanation is going to be governed either by effective nuclear charge or how far away the valence electrons are from the nucleus. Both of these go back to referencing Coulomb's law that we did in the last podcast. Right? So the trend itself is not the explanation. You do not say, this has such and such a value because it's farther to the right on the table. That's a no-go when it comes to explaining. So let's look at our first trend, which is going to be atomic radius. Atomic radius is a very easy thing to define, right? Radius of a circle is the distance from the center to the outer edge. Just like for an atom, it's the distance from the center of the atom, which is our nucleus, to the outer edge, which is the outermost part of the valence electron cloud. And this radius has a couple of different trends based on 2 directions that we can go in. Now I'm going to ask you to keep in mind 2 portions of the periodic table. Keep in mind the upper right-hand corner of the table, and keep in mind the lower left-hand corner of the table. These are going to be the 2 extremes that we're going to use to base all of our trends off of. So our first trend is as you go from left to right across the table, the radius decreases, the atoms get smaller. Again, when we compare things going left to right, we use effective nuclear charge, and what we're saying is as we go left to right, so again I'm going to use my carbon and my chlorine, because chlorine has a higher effective nuclear charge than carbon does, +7 to +4, the chlorine nucleus has more attraction to those outermost valence electrons. Right? And if it has more attraction, attractive force, that means it's going to try to clamp in a little bit more tightly on those electrons and pull it in closer to itself. So the chlorine atom will actually be smaller than an atom in the same period farther to the left. The other thing we need to pay attention to is we need to pay attention to how you go down, and as you go down a group, the radius increases. Right? As you go down a group, you add on more and more energy levels, and those higher energy levels are farther away by definition. Right? So lithium has 2s highest energy level, whereas sodium has 3s, potassium has 4s. The higher energy levels mean, if we go back to our Bohr diagram, more rings. More rings means farther away. Right? So that's our definition for radius and our trend. Our second trend is going to be ionization energy. Ionization energy is just saying how much energy do we have to add to remove one valence electron from an atom. And the amount of energy is proportional to how tightly held the electron is. The tighter an electron is held, or the harder it is to remove, the higher the ionization energy is going to be. Easy to remove electrons require very little energy put in. And our trend, again, as we go from left to right, ionization energy increases. As effective nuclear charge gets bigger, that means that the nucleus is going to hold on to those valence electrons a little bit more, which means that you have to put in a little bit more energy to actually get them pulled off. And as you go down the table, ionization energy is going to decrease. Electrons that are farther away from the nucleus, using Coulomb's law, are less attracted. And if they're less attracted to the nucleus, it's easier to pick them off. right? So again, that's our trend with ionization energy, just removing an electron from an element. Now, that describes how to remove one electron. What about if I want to remove more than one electron? Because we can certainly do that if we had enough energy, right? So as far as multiple ionizations, so second, third, fourth, whatever number of ionizations, for every electron you remove, removing an extra one requires a lot more energy to get it to go. Right? So let's say it takes me 300 kilojoules to remove one electron from an atom. To remove the second electron after I've removed the first may take me 600 or 700 kilojoules. Right? The third one might take me 1400 or 1500. It keeps increasing every time you want to remove an extra electron. That's primarily because as you do that, the effective nuclear charge remains the same because you have the same number of protons, but there are less electrons in the valence shell to take up all of that charge. So each positive charge in the nucleus gets to attract a little bit more of that electron, holding it a little bit more tightly and making it harder to remove. And also, a really cool thing that you can do, and something I'm probably going to ask you on tests and quizzes, is I'm going to give you a list of ionization energies for an element and ask you, how many valence electrons does it have, or identify this element. You can do that very easily. If you look at the chart, look for the huge jump. It's going to be like a rapid increase in ionization energy from one electron to another. If jumping from the second to the third electron removed requires a huge increase in energy, that means that that element had 2 valence electrons to begin with. The reason why is, remember, noble gases have filled valence shells. They don't want to lose electrons, right? So it's going to be really hard to pull from a noble gas. And as an example, I have a diagram coming up right here. If we look at this, I'm just going to, for sake of argument, pick magnesium because it is a 2 valence electron element. First electron to remove, 738 kilojoules. Not really that bad. Second electron, 1450. Again, we can manage that with not really much of a problem. You want to remove the third electron, though. It jumps from 1450 to 7700. Right, so it becomes significantly more difficult to remove that electron. And since it happened between the second and third electron, we can infer that magnesium has 2 valence. Aluminum, 3 valence electrons. Look what happens after the third one. It goes from 2750 to 11,000. Right, that huge jump after we remove our last valence electron to removing another one after that. Right, so this is what you can kind of do. And I mean, if you take a few seconds to look at the table, you can kind of see how these patterns laid out and how you have that gigantic jump. So that's our second of 3 trends. Our third of 3 trends is electronegativity. Now, if ionization energy is about removing electrons from an atom, electronegativity is about gaining electrons onto an atom. The technical definition for electronegativity is how attracted an atom is for electrons in a chemical bond. So if I have a water molecule, I have oxygen bonded to hydrogen. The oxygen and hydrogen atoms are sharing the electrons, but one atom is going to be more attracted than the other atom is. And the atom that's more attracted has a higher electronegativity. As you go from left to right on the table, electronegativity increases. Higher effective nuclear charge means you can have more attraction for electrons, therefore it's easier to add. As you go down, electronegativity decreases because the electrons get farther and farther away, so if there's less attraction for adding an electron that's farther away, there's less benefit for doing so. The atom really won't want to pick up that extra electron. You know, something like cesium really doesn't want to pick up an extra electron because it's large enough as is. What's it going to do with another electron, really? And if we go back to our periodic table, so atomic radius, smallest atomic radius would be helium, farthest to the right, farthest to the top. Largest radius would be francium. Those are our 2 little regions that we have to work with. Electronegativity doesn't work quite the same way for one small little thing. Noble gases, being helium, neon, and so forth, don't want extra electrons, so we assume that their electronegativity is 0. Now, if you have your periodic table out and you look in, I believe it's the upper right-hand corner, you'll see a decimal number. For fluorine, it should say 4.0. For oxygen, it should say, I believe, 3.5-ish. That number is the electronegativity of the atom. Fluorine is assigned the highest electronegativity at 4.0 because it's the smallest element that actually wants electrons. Right? And if you go down to the bottom left-hand corner, you'll see that francium has the lowest electronegativity at 0.7 because it's so large it doesn't really want to pick any more up. And this last slide that I have here is just a nice little diagram. Now notice we didn't go over all the trends in this diagram. We didn't go over metallic character. We didn't go over electron affinity, right? So you don't have to draw those in, but you should kind of draw in your notes the table which shows atomic radius, electronegativity, and ionization energy, right? So take a couple minutes to do that. And remember, when I start asking you questions on this, the trend itself is not the explanation. Don't say fluorine has a higher electronegativity because it's farther to the right or it's higher up on the table. Fluorine has a higher electronegativity because it has a higher effective nuclear charge, meaning that it will more easily accept an extra electron. Alright, so that's it for this section of notes. If you have any questions, I will see you guys later on in class. And that's pretty much it.